what I remember doing, which may not be what we did do, but I remember that, didn't we finish off by looking at stem and leaf and how you create them? Was that the last thing we did? Yeah, okay, so I'm in the right place. So exploring features of data. And the features we're talking about are, what kind of shape does it have, right? Is it skewed left or approximately skewed left, skewed right, or symmetric, sometimes called bell-shaped? And does it have outliers? And also a little bit about how do you create them, right? So for instance, how do we create stem and leaf, and how do you read the numbers off? And that's where we left off. So I want to spend the rest of this time looking at a couple of other distinct shapes. So it's going to be dot plots, right? Okay, and put that just to remind myself. We're going to look at dot plots, and we're going to look at what are called box plots. Right, let's look at, and as an example, dot plots. Suppose you have a set of data right, and it goes on and on forever, right? You got a whole set of data. The way you construct a dot plot is basically you just have like a ruler, and you start at the smallest number and you finish at the biggest number, obviously. So let's suppose you might start at 30 just because it looks good. Then you go 31, 32, 33, and you basically just draw a ruler with whatever scale is appropriate to the numbers that you've got. And then if you do a 31, you put a little circle or a dot. And 32, you might have 3 of them, right? 33, you might have 5 of them. And then 34, you've got this. And 35, you've got this. And 36, and then maybe you don't have one of them. Then you have a 37, maybe way over here, you've got a 41. You see, it's a very primitive diagram, isn't it? It's a very kind of do it in a piece of paper and you're not being particularly careful. But nonetheless, if you have a set of data, can you imagine you could create a dot plot for it? One of the things about dot plots is, do you notice that you have to do it for single numbers? They don't really work well when you combine the data. You can't really do an interval dot plot, at least I've never seen one, right? But it does do the job of shape and outliers, doesn't it? For instance, if you look at this shape, and I kind of like to draw things like that, okay. Would you say that the shape has got a distinct, maybe at least, skew to the right? Okay. If you wanted to do a dot plot, wouldn't you look for outliers in the same way? This picture is not very good for that. So can you pretend that this is a dot plot and it went like this? And then way over here at the little dot on its own. Wouldn't he be an outlier? And if my dot plots look like that, we'll call it symmetric. If my dot plots look like that, it's skewed to the right. And if my dot plots look like that, it's skewed to the left. Would you agree you'd be able to tell, even in a badly drawn dot plot, the shape, if it has one, right? And we're sticking to the rule, nothing's perfect. So things are mostly going to be approximately normal or slightly skewed to the right. You know, they'll qualify it with a word like that, perhaps. And we've already...
Except for you, sir, because you informed us yesterday that you were perfect now.
I'm perfect, yes, but dot plots are not, right? So you got to distinguish between the two. My wife just thinks that I'm conceited, not the perfect part. I also think I'm cute, but you know, what do I know?
Professor?
Oh, you're not going to, Robert, you better not agree with that last comment.
No, I had a question regarding dot plots. Would this information would it be usable for categorical data or only quantitative data?
Only quantitative data. In fact, categorical data has, for the most part, left the building. We're not really going to deal with categorical anymore, mostly because it's so hard to do much with it, right? Once you've drawn a picture and said more people like pink or something, there's not as much analysis that we can do. So we tend to focus on quantitative data. But you're right, that's a good question. I think that's about it for dot plots, really. Is there anything that you'd like to see? Okay, well, let me show you the one and only question that they've got on dot plots in that homework, just so you can get an idea of what you're expected to do. And if I kick over, here we go. In question 8, you've got this guy here, which means that we're going to be doing a stem and leaf. Remember those guys? Right. Well, actually, since I've got it here and it's not that big, let's just do that as an overlap, a bit of practice, right? So if I screw up, tell me about it. I'll do a 6 there, 85, 69. Might take me a little while, but I'll get there. 96, 86, 93, 86, 93, 55 and 86, 55, 86, 84, 81, 80, 84, 81, and 80, 61 and 69.
91.
61, thank you. I made a mistake there. 91, 85. This is kind of what you'd be doing if you were doing this question right now. I think there was another 76, isn't it? Yes, 76. Now, that's 99% right, but there are a couple of things I need to change. What do you think I need to change? The important thing I need to change, just to make it perfect.
Put the values in order. So for 80, move 80 to the beginning, 81, then 85, and then for 84, 85, 86, as far as the numbers.
Yeah, that's exactly what you do. So that's me fix that one. In this one, what do I need? A 0, 1, a 4, and another 5. So a 0, a 1, a 4, and a number 5. And that means I can get rid of those guys. And this one, what do we? 1, a 3, and a 6. The other thing is, did you notice that this one didn't have 2 versions of the stem? You know, the earlier questions had 2 5s and 2 6s and 2 7s and 2 8s. Have you noticed this only has a single 5? And it's a minor difference, but in fact, in a way, isn't that easier to do because of that? You're a 50 something, right? You're not a 50 to 54 and you go in the first 5, and a 55 to 6, 59 and you go in the second 5. You see in these ones, a single 5 covers everybody, right? So that was kind of helpful. If you, oops, I guess I should put a space here. If you turn your head on your side, which I'm giving up doing because it hurts my neck, symmetric, skewed left, skewed right.
Skewed to the left.
Correct. If I took that thing and turned it this way, can you see it's going that way? You might want to stick the word roughly in front of it, and that's fine if you want to. Now, here is the only dot plot question. This data has been made into a dot plot. Now, if you take each of the numbers, I'm not sure, well, I guess I can find the right answer and then we'll figure it out. If I take the first number, it's 55. So that one works. That one's no good. That one's no good. That one could be. So it's either this one or this one, because I think both of them have a 55. Did they have a 50? No, they don't. Isn't that a 54? So I've already finished. That's the only one that works. And I got it on the first number. If I had 2 diagrams where the first number was right, wouldn't I move to the next number, which is 61? Would you agree that dot's at 61? And then the next number was 69. Would you agree that dot is 69? Now, when I look at this dot plot and I look at this stem and leaf, in my brain, isn't it a bit easier to see the shape of the stem and leaf? when I look at this dot plot, isn't everything kind of almost nobody, one or two? And it's the shape can be destroyed, right? So, you know, if there's a lot of data, that won't be a problem. But if you've only got like 12 numbers, can you see a dot plot probably isn't going to be your friend, right? It's not going to allow you to tell. In fact, I'm convinced on this one that nobody's an outlier. Would you agree? It's pretty clear there aren't any outliers. Can you see this one? Yeah, I'm pretty sure there's not an outlier, but can you imagine these dots could end up being a little bit further apart, in which case you might falsely identify something that looks like it could be an outlier and maybe it isn't. Are we okay with dot plots then? We don't do a lot of them. That's what they do. They're quick, they're easy, cheap and cheerful, right? They get you something that you might be after. You're not going to do too much with them. Let's look at the last one on my list then, a box plot. Well, you already know half the things you need for a box plot. All box plots start with the numbers from a five-figure summary. And what we do is we use the numbers from a five-figure summary to help create this shape called a box plot. So let's suppose I had some data and it was the ages of students in the class, and I had a 16-year-old, that was the youngest I had. This was 20. Q2, which is also called the median, actually more commonly it's called the median. Let's suppose that was 25. Let's have Q3 as 39. And let's have the maximum as 69. Right. So there's your classic five-figure summary. Remember I showed you on the calculator how you get a five-figure summary using your calculator if there's a lot of data. Let's suppose I did that, right? Now I want to draw the box plot for that guy. You start off much the same way you do your dot plot. You do a ruler. And make sure that your ruler doesn't write these numbers down. All you do is you look at the smallest and the biggest. And I'm going to start at 10 because that's a nice number. And I'm going to finish at 70, right? And I'm going to go 10, 20, 30, 40, 50, 60, and 70. And will you pretend that I had square paper and I used boxes to help me get real intervals, right? They're all meant to be the same size apart. And the first guy is 16. So 16, if I put a little, where the fives would go in the middle to help me. 16 is about here, right? And very often you'll see people in diagrams write the number down if it's a bit hard for you to see. And then Q1 is 20, and we do a guy that looks like that. Oh, darn it, I can't draw. Okay, to make my information accurate, can we pretend that says 21 now? I don't want to change my picture. 25 would be here. And 39 would be way over here. And 69, oh, it's 39. And then finally 69 would be here. And you join these guys together. And they make the box. And then you draw a big, long, skinny line to here. And a big, long, skinny line to here. And that is a box plot. Do you see the 5 numbers that make up the 5-figure summary are where you put each of these features? Has anybody ever seen a box plot in, I don't know, a geography class or somewhere? Ever seen those shapes?
Yes.
Can you recall where you noticed them?
Economics class.
Right. So it's a picture, it's a diagram that is very often used to visualize data, right? Because can you imagine that this data might have came from 35 students, Isn't it much nicer to see the picture? Now, you've got to be able to interpret this picture. In other words, what does the shape of the data look like? Well, when it's a dot plot or a histogram, don't you get the height and the distance and the width and all that? It's pretty easy to see, but I can still interpret it. I'm going to ask you the question, and if you can get it, that's great. Is this data skewed right, skewed left, or symmetric?
To the left?
Nope.
No.
I'm not only guessing, you know what I mean?
Well,
It might be the right answer, but the wrong word.
I was basing it on your little red line here going out to the left, right?
This one here, or this one here?
Where the first number is, right? Yeah.
Right, there? Okay. When we look at this shape, do you notice that from the middle going this way, isn't that stretching to the right? Can you see that? And do you see the other side?
No, I can't see it because my screen is blocking that last part. So okay, yeah, now I can see.
Okay. I don't know. Does that help any?
Yeah.
Okay, there we go.
It helps when I can see the whole thing. Sure.
It certainly does. So if he was seeing that, you can imagine why you might have picked something else, right? But can you see this now? It's skewed to the right. So how do you look at a box plot? What I do is I look at two distinct things, and if they both match, I've got my name. This central part, right, from 21 to 39, right, from here to here, that's where the middle 50% lie. And then this bit and that bit, that's where the tails live. So if you see the box in the middle, right, the middle 50%, do you see that it's bigger on the right than it is on the left? Do you see the split? Bigger on the right than it is on the left. Do you see the tail, especially the tail? That's a very good guess. Do you see it's big on the right and not on the left? So that would be skewed to the right. How about me just showing you some baby pictures, and I'll show you the three situations. Can you see the three situations that would generate symmetric, skewed right, and skewed left? Badly drawn. Would you agree that that one's equally balanced in the middle? The box is roughly half and half. And would you agree that roughly the two tails are about the same length? That's what symmetric looks like. Would you see in this one, although I'm not so convinced, maybe I should have done that a little bit better, but isn't the box slightly bigger on the right than it is on the left? And would you agree the tail is definitely bigger? And that would be a skewed to the right. And in this one, I think I did a better job. Would you agree that the box is bigger on the left and the tail is bigger on the left? And that would be skewed to the left. So if you do a box plot, you can, with a little bit of practice, identify whether the entire data set is likely to be roughly symmetric or skewed left or skewed right. Does that seem reasonable from the picture now that you kind of know what to look for? Right. So here's some just to throw you. Imagine I did a box plot. And it looked like that. Hey, the tail is really big on the left. Uh-oh. But the box is really big on the right. Yep, that could happen. If that does happen, well, I guess I should say there's no name for it, right? Right? It has no, it's not skewed left, it's not skewed right, it's not symmetric. Would you agree it's just some weird you know, up and down data that nobody knows a name for because we haven't bothered to give it one, right? So there are technically 4 answers, isn't there? You've got no shape at all that has a name. You're skewed left, you're skewed right, or you're symmetric, right? I don't think we've had many questions where the data didn't have a name, but you know, it was one of the 3. But can you imagine there might be a situation where the data is just kind of random and there is no pattern, right? So it's got no shape. And that would be a box plot that would have that kind of feature, right? There's nothing interesting going on as far as shape. Are we good?
I have a random question about the no name.
Uh-huh.
Couldn't
That's my name for it. It's got no name.
Well, no,
Yes.
couldn't the no name have an outlier and that's why it's like that?
It could be easily. Yes. Which kind of nicely brings me to this. Box plots are very difficult to identify if somebody is an outlier. If all I tell you is a 5-figure summary, that 69 could be an outlier, couldn't it? But couldn't that 69 just be a normal number because the next one to it is 67? That is less likely to be an outlier because of the proximity of Q1. But would you agree on this side? Box plots are not good at identifying outliers. The only way you could identify an outlier is if somebody gave you all the numbers that they used to make the box plot, and then you could look at the raw data and say, oh, that 69 is unusual. The next person, you know, the next person's 42 years old. And then you could identify an outlier that way. So box plots are not good at identifying outliers yet. But we are going to show you, I keep promising, but I haven't produced the promise yet, that we will give you a test that you don't need to guess on outliers. And that test can be used on box plots as well. So that's going to be helpful. That way we don't need to say, well, I can't really tell, or in a histogram situation, it might be, I'm not 100% sure, it might not be. We'll do away with that by having a little test that says, if you're bigger than this number, you're an outlier, and if you're not, you're not.
I have a question. I think
Yes,
I missed
James.
something. What is the difference between the no name and then the skewed left box plot?
Well, the difference in this picture, let me put the 2 of them together. This one is skewed to the left. Now this one is skewed to the left because the tail is big on the left and the box is split. And the box is split so that the left-hand side is bigger than the right-hand side. Now, the one that's got no name, would you agree that the tail is big on the left? But do you notice that the box has been split the other way? Do you see the box is now big on the right and small on the left?
Yes. Yeah, I get that now.
And so
Thank you.
that's a kind of contradiction, isn't it? For you to be skewed, shouldn't everything be skewed left or everything be skewed right? You can't have a bit of both because then you're not really skewed anymore. Are we good with that, guy?
Yes, thank you.
Right. So let me, I'm still working on 5-figure summaries. Talk a little bit about some other information that you can get from it. I've got this guy. I just want to write him down again because I'm going to be writing all sorts of stuff down about it in a minute. These guys, right? These guys here, right, from this data, they're called, you might think that's a funny name, quartiles, but it's really not. If you think about it, isn't the data split into 4 pieces? Right? The first quarter, the second quarter, the third quarter, and the fourth quarter. And doesn't quartiles sound like a good name now for those things? The Q1, the Q2, and the Q3. Even though there's 3 of them, they break the data into 4 pieces. So if I went and said to you, what age were the youngest 25% of the class? what age range? You would say 16 to 21. Would that make sense for the youngest 25% of the class, right? The youngest a quarter. What age group would you be in if you were in the oldest 1/4? What would the age range be for the oldest 1/4?
39 to 69.
Correct. What age group would you be in if you were in the middle 50%?
'21 to 39.
Does that make sense? The middle 50%, which would be that group there. So the middle 50%. Now I'm using percentages here, but couldn't they have also used fractions? Like the middle a half, the top 1/4, the bottom 1/4, right? In this case, it would be 21 to 39. And then you can do all sorts of other combinations, you know, oh, I don't know, like what age would you need to be so that everybody, so at least half the class was younger than you? And you'd say, well, you'd need to be 25. What age would you need to be so that 1/4 of the class was younger than you? You would say 21. What age would you need to be so that 3/4 of the class were older than you? The answer would be 39. So do you need these quartiles? You can phrase that question in a variety of ways. Is that helpful? That, you know, it gives you that kind of very rough idea of what the heck is going on. I think I only have a couple of questions to do at the beginning here, if I recollect. Yes. And then we will moving on. We'll finish our section and we can get a head start on what's going to happen next week. I like that, right? Makes life easy if you know you've got everything that you need to do for this coming Sunday. Okay. Can you see that big box at the top is the way WebAssign gives you 5-figure summaries? Right. Me personally, I would prefer you just said min equals, you know, the way I wrote it down on paper, right? But that's fine. Would you agree in this one, the minimum is 57, the maximum is 73. Q1 is that guy. There's your median. And there is Q2. I think of it as a big loop, right? Minimum Q1, Q2, Q3 max. You see the loop I'm talking about, right? That's how I would read it. Now, once you've got that in front of you, couldn't you do a box plot from that data, even although they never asked you to? Isn't that the only 5 numbers that you need, right? They go on and ask you, what interval would you be in this and what interval would you be in that? So I'll just pick one at random. What is the interval of heights? So I guess these are inches for female students. What interval in heights, in inches, contains the middle half? Okay. The middle 1/2. From what number to what number?
63.1 to 68.
Agreed. Isn't that Q1?
Yes.
And this guy over here is the other one, right? Are you getting a little bit more comfortable about what this 5-figure summary can be used to identify, right? You can figure out who the middle is, the range of people in the middle half. Can you also do the top 1/4, the bottom 1/4, and any other combination your brain can think of? What you can't tell from that is outliers, if there are any. Would you agree? Unless you give me more information, I can't tell you about outliers, which is why they don't ask you, right? They're not going to ask you something you can't answer. So if you wondered why some questions had outliers, an outlier question in them, and why these ones don't, that's essentially the reason. Are we comfortable with this guy? Right. And we've done all the others, so unless we have any more questions, can we call this one stick a fork in it? It's done. Right? We good? Last chance, and then you want to ask, this is your chance. Okay. So we're now ahead of the game. So all you need to get done for this Sunday is up to this chapter here that we've just finished doing, right? So remember to do that one at the top. A lot of people think that's not homework, but it is, right? That web assigned salt stuff. Does it take about 15 minutes to do that? It's very quick, isn't it? Those who've done it longer? About 15? Right. It's not a biggie, hopefully. Right, we're now going to look at numerical summaries of quantitative data, and that's going to be all notes. So I'm not going to need WebAssign. We're going to
I'm
be
sorry, all what?
notes. I'm going to be writing down things and telling you things, right? So you might want to get ready for that. I'll also be doing some calculator stuff. So put my heading, chapter 2. And we're going to be looking at numerical summaries. Numerical summaries fall into two groups. The first group is essentially one that we're quite familiar with, 5-figure summaries. So there's nothing that different. Basically, we take data and we summarize it. Excuse me, I'm trying to close some windows here because it's distracting me. And the second summaries, we haven't done anything really on, but they're going to be mean, standard deviation, and range. So we have 5-figure summaries, we have means, we have standard deviations, and we have ranges. And that kind of basically covers all the possibilities of our data. And the ones that I'm going to focus on are 5-figure summary, because they're the ones that we're really familiar with. And I'm going to do a set of data and just build it from scratch. And then I'm going to use the calculator. And then I'll add some things that we haven't used them for. So no particular reason, I'm just randomly writing down my data and hopefully it works out well. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Okay, so I asked a class of 14, how many siblings have you got? And this is the answer. Okay, that's a weird answer, but it's a number, right? Somebody's got 19 siblings. That is not the world record, by the way. Do you know, the world record for the greatest number of siblings, at least in history, is a lot more than that. So that's what we have. So from this data, I'm going to do it by hand one more time, and then we'll do the same guy on calculator, just so we can collect the 5-figure summary. So that's some that we've kind of done, it's an overlap, and that's fine. I have chosen a slightly different data set. I've chosen an even number, 14. Now, half of 14 is 7. And you would say, okay, 1, 2, 3, 4, 5, 6, it's that guy, right? But if you go 1, 2, 3, 4, 5, 6, 7, it's actually that guy. Do you notice that when you have an even number of data points, there's 2 guys in the middle? You remember when it was 7 numbers or 9 numbers, life was easy. Wasn't there one guy in the middle and that was easy? It was him, right? What do we do you think, when you try to calculate the median and there's two numbers.
The average of the two.
Exactly. So I forgot to write down the two obvious ones. Would you agree the minimum and the maximum are never a problem, right? So if you average these two guys out, would you agree that the answer for the median is 5 point, I don't know where that 5 came from, it's 5.5. Right, we're almost done, aren't we? We're 3 out of the 5. So now I have to figure out who Q1 is and now who Q3 is. When you have an even number of numbers, 5.5, what you do is you imagine where 5.5 would go. Wouldn't it go right between those two numbers? You see it going right between the two. Now, what that does now is it splits my data into the big half and the small half. Now, do you see, including that 5, do you see that the big half has 1, 2, 3, 4, 5, 6, 7 numbers? So which of these numbers here is the middle? Well, there are 7 numbers. Would you agree it's number 3? 1, 2, 3, 4, 5, 6, 7 numbers. Halfway is this fella here. There's Q1. Right, if you cover this up, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, it's this guy. 1, 2, 3, 4, it's this guy. That's Q3. So Q1 is 3 and Q3 is 10. Are you comfortable about, for small data sets, how to find the 5-figure summary? Min and max, then you go median, and you split the data into left and a right, small and a big. And the middle of the little guys is called Q1, and the middle of the big guys is called Q3. Is everyone looking good? Right. Now, I'm going to put that same data into the calculator, and we may get slightly different answers. And that's because calculators and WebAssign and people like that are not very good at it. Building little walls and calling it the middle probably isn't very easy to program. So I'm going to go to start, I'm going to go to edit, and I'm going to type in my numbers. So it's going to be 1, 1, 2, 3, oops, 4, 5, 6, 7, 8, 10, 12, 17, and 19. Right, so I put all my numbers in. Hopefully I got them all. Did I get them all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, I missed somebody. Two ones, good. 2, 3, 4, 5, 6, that's good. 7, yep. 8, 10, 12, 17, 19. Okay, I thought I'd miss one. Evidently I hadn't. All I do now is I hit start button. I move over to calc. I choose one variable statistics, and I tell it to find the data in L1. And if I scroll down, the minimum is 1. Do you see there's a little difference in my Q2? Do you see they're calling it 2.5? Do you see my median? Is 6, and my Q3 is a little bit off, and my max is 19. The calculator doesn't do a great job of these fellas. It's good half the time, and it's pretty close the other half. So I'm going to use this one. So what you're going to do if you are doing this same question and you're doing it in WebAssign, WebAssign has a salt button, and you hit the salt button and you just let it calculate it, and whatever it says they are, you write them down. So it's not a biggie, right? So when you come to do the homework, you're going to hit the salt button and you're going to do that. So you won't need your calculator to do that, but I wanted to kind of do it that way. So we'll assume that my numbers are better, which they really are. And now
Sure.
we're going to, yes.
I'm sorry to interrupt. I think what happened was that you left out the second 5.
Ah, okay. I like that. Let's see if I can fix it.
Thank you for saying something because I got the same answers and I didn't get the same one he did. And I was like, what did they do?
Nothing. The good news is if you forget a number, just tag it on to the end. And by the way, that was after me checking it, wasn't it? I still missed it. Okay. So start, calc, number 1, blah, 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 do all that. Scroll down to the bottom. And hey, I take it back. Calculator got it right this time. Even better. Bear in mind what I did say does happen, right? There will be times when you do the calculator and it's a little bit out. So perfect that it agrees. So I'm going to do something different with this data that we haven't done yet. There are 2 types of measurement that we're going to focus on in this section. We're going to look at what you would call, what's the typical number in the data set? What's the, in this case, what's the typical number of siblings in the family, right? And we call that a fancy name. We call that number the measure of center. And then how spread out is the data? Is all the data really close to each other or is it all over the place? And we have a number for that, and that is called the measure of spread. Now, for 5-figure summaries, the measure of center is the median. Does it seem reasonable that roughly somewhere in the region 5 to 6, and we're calling it 5.5, and I know that's a bit silly, but that's where the roughly in this class, that's roughly the number of siblings. Now, although you cannot get 5.5 siblings, that is still the number that you use. But I think you'll have seen this before. Haven't you heard things like the average family size is 2.2 children? You heard that kind of deal? Now, you all say, wait a minute, you can't get 2.2 children. I agree with you. But isn't that a measure of roughly where the middle is? Right, the typical family is about 2 and occasionally 3, right? That kind of idea. So it's a number that gives you a kind of ballpark figure for the typical person in the data, right? And that number doesn't necessarily have to exist in real life. You can't have 5.5 siblings, but isn't it still measuring roughly where the middle is, right? About 5 and a bit. Now, the measure of spread, right? How spread out the data is Q3 take away Q1. So in this case, 10 take away 3 is 7. And this measure of spread is called the interquartile range. So if you've ever heard the term or read it and wondered what it is, the interquartile range. And what that is telling us is that the difference between the middle of half, right, from here to here, that difference is about 7. That's the interquartile range. Now, if that number was 2, can you see that the middle of half are almost everybody's about the same number of children, right? If the interquartile range was a small number, it means the data typically isn't spread out that much. At least the middle half isn't, right? And if it was 42, wouldn't it be all over the place? So imagine I have 2 classes in, and I'm going to use these 2 numbers to try and identify what the classes are doing. I'm not even going to tell you the 5-figure summary. I'm just going to tell you these 2, what are called numerical summaries. Statistics is another name for them. Here are my 2 classes, A and B. And I gave them a final exam. And the median of this class was 70. And the median of this class was 50. And the interquartile range of the first class was 10, and the interquartile range of the second class was 20. And that's all I've told you about these two classes. But I can actually make some pretty intelligent conclusions based on just those summaries. Let's start with the first one. Which of those two classes did better in the final exam? A or B?
A.
A. Would it seem reasonable that if you've got a bigger median, the typical person in the class was probably going to be in the 70s, right? Close to 70 anyway. On the other section, wouldn't they only be in the 50s? Would that be that would be evidence at least that class A did better. Now, the interquartile range is telling me something different. It's telling me how spread out the scores were. Would you agree in class A, not only did they get about 70, but didn't they not vary that much away from 70, right? For instance, won't the middle half have got somewhere between 60 and 80? Right, they're pretty close together. Now, what about this poor class here? Well, since the interquartile range is much bigger, doesn't that mean that these scores are much more spread out? Right, people in this class, not only did their average get you 50, but weren't they all the way down to, I don't know, the middle half anyway, weren't they all the way down to 30 and all the way up to 70? And so you get a very good idea of spread, you see. Big IQR, big spread. And normally it's helpful to have two groups that you want to compare, because then these things can really be compare and contrast a lot better, right? Okay. Now, suppose I have two machines, I'll call them A and B, and they're meant to be producing cornflakes, and they're meant to be producing boxes with 16 ounces of cornflakes. So you can imagine the cornflakes are made and they go into a big hopper, and there's this machine that puts them into the box, right? The plastic bag that goes in the box, and it's got some kind of mechanism where it figures out, you know, weight, you know, close the box. Next one, weight, close the box. You might one of those automated things. And they've got two machines. And this is the data that we get. And this fella is 16 ounces, and so is this one. But this one is 2 ounces, and this one is 0.2 ounces. Right? Now, both machines are on average generating 16 ounces in a box, right? But you know, you can imagine nothing's perfect, right? Sometimes there's a little air gap and less gets in, and sometimes some of the cornflakes are stuck together and they're a bit heavier, right? So you get a little bit more. But on average, don't you get the right number in both machines? So what is this telling us about the machines? The interquartile range.
The lower the number, the more accurate it is.
Yeah. So isn't this machine a good machine for making sure that you give accurate? Nobody wants to get a box of cornflakes that sometimes has 14 ounces and then sometimes has 18 ounces. Isn't that inconsistent? And people don't like inconsistency, right? If I buy a box of cornflakes, I want to have 16 ounces in it, right? I don't want to be a lucky dip and one day I get lucky and the next day they shortchange me, right? I don't want that. So we would probably want to use this machine. And wouldn't this probably be an indication that maybe this machine needs some maintenance? Maybe it's, you know, got some going on with it, and, you know, some spring needs to be replaced or whatever it is that's causing the trouble. So that when you do quality assurance, right, when you're in a factory and you're doing quality, isn't that one of the things you would do from time to time? Just check out everything that you can. Weights is one of those measures. And you would say, okay, that machine needs to go and get fixed because it's not doing its job. And here's my last version of this. We were talking about basketball before the conversation began. So I'm going to make up numbers, Don, because I have no idea what real numbers are in basketball. But I believe there's a penalty shot where if something happens, you get to throw it, right? And we're going to look at two players, A and B. And we're going to look at the median in both cases. And just to make my life easier, both of them got 50 penalties last year, right? So both of them got 50 shots each, right? So I'm comparing like we like. And this guy here got 25 of them, and so did this guy. So right now, would you agree both players are just as good or just as bad at getting penalty points? But then I looked at the interquartile range, because you know you get 1 shot, 2 shots, that kind of thing. Let's suppose they did. And this fella had an interquartile range of 2, and this guy had an interquartile range of just 1. What are these numbers telling you about the players? How?
A, the penalty shot more than B does.
Well, one of them's more consistent, isn't he? Right. I should probably have done penalty shots. Can we pretend that's the number of points they get in a game? That may be a better number, right? Both of them get 25 points in a game, but this guy has an interquartile range of 2, and this guy has an interquartile. Let's make it worse. Let's make this guy's interquartile 10, and this one is 1. If you play this guy, won't you get 25 points off him a game, give or take 1 or 2, right? He's pretty Mr. Consistent, right? I've changed the game now, right? 25 points a game. If you play this guy, yeah, on average, won't you get 25 points a game? But sometimes he's going to play out his skin and get you 35 points, isn't he? And sometimes he's going to have a stinker of a game and he's only going to get you 15 points. Now, if you're a manager and you can only play one of these, wouldn't that second piece of information help you decide what you want? See, if you're playing a team that you know you're probably going to beat most of the time, won't you play safe and play Mr. Consistent? Right? If you're playing against a team, you're pretty sure you're going to beat most of the time. Play Mr. Consistent. Suppose you're playing the team that's going to win the league if you're not careful, right? Might you risk playing him just in case he has a really good game? Because if he has a really good game, couldn't you end up winning? Now, if he has a really stinking game, won't you get beat? But if you play him, won't you probably get beat anyway? So what's the problem, right? You got to risk it sometimes, right? So you can see how you could use these numbers of the interquartile range gives you an idea of one of the things it does is consistency if you're talking about sports.